Section 3.1, Linear Equations and Rectangular Coordinates. In this section, we're going to look at linear equations in two variables. And that will be the theme of this chapter, really. Let's start with the definition. Here on page 201 in the brown box, it says a linear equation in two variables, here x and y, can be written in the form ax plus by equals c, where a, b, and c are real, and a and b are not both 0. Notice that this form is called standard form. That'll be important to us later in other sections. So, what does this tell me? A, b, and c are real numbers. X and y are the only things that are going to be variables. We'll be replacing a, b, and c with numbers. And it says a and b are not both 0. That means at least one of those variables has to be visible. Notice also in this linear equation that my variables are raised only to the first power. X to the first, y to the first. No x squared, no square root of y, no variable in a denominator. And so once again, linear telling us that my variables are raised only to that first power. A very simple example would be x plus y equals 5. The coefficient on x is 1. The coefficient on y is 1. The numeric term is 5. Those are all real. My variables are raised only to the first power, so here I have a linear equation in two variables. Anytime we talk about equations, we talk about their solutions. When it comes to an equation in two variables, we need two values to make a solution. A solution is going to be values that I can plug back in for the variables that make the original statement true. For example, this basically says I'm thinking of two numbers x and y that add up to 5. How about 2 and 3? When x is 2 and y is 3, that's a solution to that equation, because plugging it back in gives me a true statement. When it comes to two variables, we have a way of writing this. We'll write this as an ordered pair. The ordered pair 2, 3, in parentheses, separated by a comma. It's an ordered pair because it's always in the same order. It is always x, comma, y. The x is always given first. Now, the thing about these equations that we don't see in our equations in one variable, these have more than one solution. The ordered pair 1, 4 is also a solution to that equation. Plug in 1 for x and 4 for y. The ordered pair 5, 0 is also a solution. The ordered pair 2 and a half, 2 and a half. Plug that in, it makes the statement true. The ordered pair -6 and +11 will make that original statement true when plugged back in for x and y. And we could keep going, but we'd be going forever. There are an infinite number of ordered pairs that will satisfy that equation. One thing we're going to be asked to do in this section is to decide if a given ordered pair is indeed a solution to the given equation. Let's look at the homework set and grab number 20. Just like back in chapter 2, they're going to start us off nice and easy. Actually, in chapter 1, we looked first at equations. We weren't solving them. We were simply checking to see if the given value was a solution to the equation. It was chapter 2 where we started solving them. So here in number 20 it says decide whether the given ordered pair is a solution of the given equation. This tells me plug 4 in for x, plug 2 in for y, and see if it makes the original statement true. I think you can already see that checks, and so yes, the ordered pair 4, 2 is a solution to this equation. Number 22. Is this ordered pair a solution to this linear equation in two variables? When x is 2 and y is 1, does that give me a true statement? So we plug in and we check. And I'm sure you can already see what's happening here. That gives me a false statement. So is the ordered pair 2, 1 a solution to the given equation? No, it's not. Look at number 26. Now, problems like number 26 are something you're going to need to get used to very quickly. My first question is this a linear equation in two variables? Is the given equation a linear equation in two variables? And the answer is yes. Because it looks like ax plus by equals c, where a, b, and c are real, a and b are not both 0. You can't see the y, and what could possibly make that true if the coefficient on y were 0? Because 0 times y is 0, added to x is just x. So our y term doesn't show because its coefficient is 0, but according to our definition, as long as a and b, the coefficients on x and y, as long as both coefficients are not 0, we can still treat it as a linear equation in two variables. That's the idea that you need to get used to very quickly. So the question is this ordered pair a solution to the given equation? How do we check? We plug -6 in for x, we plug 5 in for y. So right here, x is -6, and there's no y, so there's no place to put the 5, and that's fine. We plug in for what we can. This gives me a true statement, and so yes, this is a solution. Think about what this equation says. This equation says x is -6. X is -6. Is that true for this ordered pair? Sure. In other words, any ordered pair with -6 for its x component will be a solution regardless of the value of y. Number 28. Number 28. Is this a linear equation in two variables? And the answer again, yes. I can see at least one of my variables, x or y. That just means the coefficient on the other one is 0, so he doesn't show up. And we want to know, is this a solution? I can right now take -6, plug it in for x. There's no place to plug in that 2. So we have -6 plus 4. Is that equal to 0? Certainly not. And so no, this is not a solution to the given equation. One thing that I like to do when only one of the variables is visible, I like to go ahead and solve it for the variable that is there. It just makes more sense to me that way. Subtract 4 from both sides. This is equivalent to x equals negative 4. In other words, if my ordered pair had had negative 4 for x, that would have made the original statement true. You'll see why I like solving this for the visible variable when we get to some of these other problems. Let's have a look at number 30. Now we're going to be asked to complete a solution. We're not being asked to fully solve, but in number 30, in the instructions it says for the equation y equals 2x plus 7. Is that a linear equation in two variables? Yes, because I see the x and the y, as long as I see at least one of them. They're both raised only to the first power. No y squared, no x in a denominator. So that's linear. And it says complete the ordered pair 2 comma blank. Well, what is this telling me? This is telling me that I want to know the y value that goes along with when x is 2. So what am I going to do? I'm going to plug 2 in for x and solve for y. Plug 2 in for x and solve for y. This just needs to be cranked out. So the ordered pair 2, 11 is a solution to the given equation. Now, when you look this up in the back of the book, all she's looking for is the 11. If you would prefer to give the full ordered pair, that's fine. Either way, I think is appropriate in this case. Either way. Let's do number 32 while we're here. In number 32, same equation. I shouldn't have erased that top line, but that's all right. Complete the ordered pair. Blank comma 0. This asks the question, what is x when y is 0? And how do we figure that out? We plug 0 in for y and solve for x. When y is 0, what would x have to be so that this ordered pair is a solution to the given equation? We plug 0 in for y, now we solve for x. Subtract 7 from both sides and divide both sides by 2. Negative 7 halves. Or if you want to see it up here in the ordered pair. And you know I will accept negative 3 1/2, but at the moment I don't see any reason to change it to a mixed number. In number 40, we're looking at the same kind of problem, except this time instead of just a single ordered pair, we're given a table to complete. So in number 40, 3x minus 5y equals negative 15. And they give us the table. We want to fill in the missing pieces of this table. In other words, when x is 0, what's y? When y is 0, what's x? And finally, when y is negative 6, what's x? Let's start with our first one. When x is 0, well, plug 0 in for x and solve for y. 3 times 0 is 0, minus the rest is minus the rest. In other words, that 0 term just vanishes, right? Because 0 is the additive identity. It leaves the rest of it alone. Divide both sides by negative 5 to find that y equals positive 3. Now I want you to look at this. I like plugging in zeros to equations like this because here's what happens. And we just saw it. When you plug 0 in for x, the x term disappears. And you are left with negative 5y equals negative 15. I think we can typically do those in our head. Divide both sides by negative 5. We've got what? Y equals 3. Let's try it on this one. When y is 0. Now, if you want to crank the whole thing out, that's fine. But here's what you'll see me do most often. If I'm plugging in a 0, when y is 0, what happens? Well, the y term is going to disappear. And so we now have 3x equals negative 15. If 3x equals negative 15, then x must be what? Negative 5. If you want to see that written out completely, go ahead and do it. But generally with those zeros, it's quick and easy work just to think about plugging them in. When I plug 0 in for y, that y term disappears. What am I left with? And it's usually a quick and easy answer. Now, when y equals negative 6, I'm not doing that one in my head. We'll go ahead and show this. Plugging in zeros, quick and easy. Plugging in a negative 6, a little bit different. Simplify. Minus 5 times minus 6 is plus 30. Subtract 30 from both sides. Watch your signs. Divide both sides by x. Divide both sides by 3 to get x by itself. Divide both sides by 3 to find that x is negative 15. And so we've completed their table. Now, in these instructions, it says to also write the results as ordered pairs. So not only are they wanting those results, but she wants them shown as ordered pairs. I'm not going to get too excited about that because this process is not an end to itself. This process of completing one of these tables is actually a small part of a bigger problem that we're going to see, well, before we're done with this section, and we're going to see a lot more of in the next section. So I'm just going to focus on completing these tables. Let's look at number 44. This is the idea I said you need to get used to quickly. In number 44, we have the equation y equals negative 6. Y equals negative 6. Is that a linear equation in two variables? Yes, it is. I just can't see the x because the coefficient on x must be 0. We're given a table. We're given a table to complete when x is 8, when x is 4, when x is negative 2. Alright guys, when x is 8, what's y? The algebra speaks if you'll listen to it. What does this equation say? Y is negative 6. And then you say, well, what about when x is 8? And the equation says, I already told you, y is negative 6. Okay, well what about when x is 4? And the equation gets a little perturbed. He said, you're not paying attention. I have already told you. Y is negative 6, and that's the end of it. It doesn't matter the value of x. There's nowhere to plug that in anyway. But what is true? That y is negative 6. So all of my ordered pairs will have a y value of negative 6. Don't make these tougher than they need to be. There's no place to plug in the x. And the equation is saying y is negative 6. That's all I need to know. Don't make those tougher than they are. When it comes to dealing with ordered pairs, we like to represent them graphically and see if there's some relationship among certain sets of ordered pairs. And for that, we're going to use our coordinate system, our rectangular coordinate system, also called the Cartesian coordinate system, named for philosopher and mathematician René Descartes. He's the guy that said, "I think, therefore I am." He's also the one credited with coming up with the rectangular coordinate system. Now, in this section, in this chapter, you may want to get yourself some graph paper. It's certainly not necessary, but you might find that it makes things a little easier. What we have here are two number lines that are put together where they are both 0. They are put together at right angles to each other. And this allows me to graphically represent ordered pairs. For example, the ordered pair 2, 3. That means x is 2, so I go over 2 in the x direction, and y is 3. Here's the point that represents the ordered pair 2, 3. This point where the number lines cross, the number lines are called the axes. This is the x-axis, there's the y-axis. This is the point 0, 0, and it is called the origin. The point 0, 0 is called the origin. Let's throw another point up here just to have another point. How about -4, -4? Okay, back to -4 in the x direction, down to -4 in the y direction, about right there. If you want nice pretty pictures, look in your book, right? Because this is as good as it gets for me on a whiteboard. There's our point, -4, -4. And notice that these two axes divide this plane, this flat surface. We're working in the plane of the whiteboard. They divide this plane into 4 regions. We call these regions quadrants, and we name them Quadrant 1, Quadrant 2, Quadrant 3 down here, and Quadrant 4. Notice that they are Roman numerals. If I ask you in which quadrant would you find the point 2, 3, you give me the Roman numeral. You give me the Arabic numeral, I'm going to count it wrong. What's an Arabic numeral? The numbers that we use all the time. If I ask you about a quadrant, you must answer me with a Roman numeral. You can see also a few figures here in your text that go along with what we have on the board. Page 204 at the bottom, figure 3. Page 205 in the middle, figures 4 and 5. We're going to have a great deal to say about the coordinate plane and about plotting points and about graphing these equations as this chapter goes on. We're going to use this coordinate plane now to tackle number 72. Number 72, it says complete the table of values for each equation, then plot and label the ordered pairs. The equation 2x minus y equals 4. The table that they've given me, we're looking for 4 different ordered pairs. 0 comma what comma 0, 1 comma something, and something comma -6. Once we find these 4 ordered pairs, we want to plot them on a coordinate plane. Alright, so when x is 0, what's y? Remember, plugging in zeros is typically very easy. When x is 0, the x term disappears. So we have negative y equals positive 4. Now if negative y equals positive 4, then y itself must be what? Negative 4. When y is 0. When y is 0, the y term disappears. And we simply have 2x equals 4. Well, if 2x equals 4, x must have been what? X must have been 2. Plugging in things other than 0, I don't often do that in my head. I want to see that work, just so I don't make a silly mistake. Plug 1 in for x and solve for y to get this third ordered pair. So we have 2 minus y equals 4. Subtract 2 from both sides and take the opposite of both sides. Or, I don't know what you want to call this. Divide both sides by negative 1. Multiply both sides by negative 1. I said take the opposite of both sides. They all mean the same thing. If negative y is positive 2, then y itself must be negative 2. And then we want to know when y is negative 6, what ordered pair do we get? So 2x minus a negative 6, watch your signs. Solve for x. Minus minus makes plus. Subtract 6 from both sides. Divide both sides by 2 to find that x is negative 1. Alright, we've got our table finished. Now she wants us to plot these points in the coordinate plane. There's a negative 6 here. Let's go out to 6 in all directions. And we want this to be kind of neat. Alright? Because in number 77, we're going to be asked a question. And it's going to depend on how well we've drawn these pictures. Again, another reason that you might invest in some graph paper. We're going to try to draw this as neatly as we can here on the whiteboard as we plot these points now. Our first point, the point 0, negative 4. 0, negative 4. That's no motion in the x direction. No motion left to right. And then what? Down to negative 4, actually here on the y-axis. Right there. And she said go ahead and label these points as well. So we'll do that as we go along. By the way, in what quadrant does that point lie? In what quadrant do I find the point 0, negative 4? 0, negative 4 is on the y-axis. It is considered to lie in no quadrant. Any point on an axis does not belong to a quadrant. So very careful when you're asked those types of questions. The point 2, 0. Over to 2 in the x direction and no motion up or down. Right here on the x-axis. There's my point 2, 0. Also does not belong to any particular quadrant. It's on the x-axis. The point 1, negative 2. 1, negative 2. Now that's down here in the fourth quadrant. Over in the positive direction 1 on my x-axis and down 2 units, down to negative 2 on my y-axis. And it's getting a little crowded for my labels now. But we'll make do. And then finally the point negative 1, negative 6. So in the x direction, back up to negative 1. In the y direction, come down here into quadrant 3, down to negative 6. Label that point. Now I'm going to stop right there. I'm going to point out that after doing number 71, 73, and number 75, you're going to be asked number 77. It says look at the graphs of the ordered pairs in these exercises, including the one that we just did. And it says, do you see a pattern? Is there any pattern we can establish? And that's why we want these figures from 71 to 75 to be fairly neat, so we can stand back and see if we see a pattern. We're going to leave it right there for now. In section 3.2, we will pick up with this same idea, but I'll let you practice 3.1 for now.